Hello, everybody. It's me, Michael Leclerc, again, here for another week of learning and environmental concerns. Before we get into today's topic, I want to just go over a couple quick points again. First off, our assignment Fighting Climate Change will be due tonight at midnight. So, tonight, as in February 11th at midnight. Please have it handed in, otherwise, it will be 5% loss for every day subsequent. Another thing, as you can see on the screen behind me here, we're going to be talking briefly about essay assignment number 1, which will be due Friday, February 18th at midnight. So next week, next Friday. It's going to be based off of global or national agreements in regards to climate change and the environment in general. So a good example is Montreal Protocol, but please don't everybody just decide to write about that agreement. Do some research, find some that might interest you and write about those. Keep them to 2 to 5 pages in length, and you can use MLA format. The link that I've provided right there will take you to a website that shows you basically everything you need to know in terms of how to do MLA format. This will also include footnotes and a bibliography. After the Fighting Climate Change, you guys should be a little bit more familiar with footnotes and a bibliography, so that shouldn't be too bad. If you don't include that stuff, plagiarism will be considered an automatic failure. And as I said, it will be due Friday, February 18th at midnight. If you guys have any other questions about the assignment, it is available on Blackboard for you guys to grab and see the breakdown of the mark on the rubric and everything. If you do have more questions, you can always email me or throw questions up in the discussion boards. I'm here for you guys if you need anything. Okay. So the next thing we're going to be talking about is the midterm. So the midterm is coming up. It's funny to think, It feels like just yesterday that we started the course. The midterm is going to be available for the entire week from Monday, February 21st to Friday, February 25th. You only have one attempt at it. So, yeah. That's all you got with it, unfortunately. There's going to be 25 questions total that are a mix of multiple choice and true and false. So it's not 25 of each, it's 25 combined. And the midterm itself will be found in the tests folder under the assignments and tests section. This midterm is worth 25% of your final mark, and it'll cover material from weeks 1 to 6. So we'll include the stuff that we're talking about this week, as well as the stuff we will be talking about next week, and of course the stuff that we talked about in previous weeks. And I hope everybody's ready for it. And if you have any questions for anything, of course, as always, please get a hold of me. I'm here to help in any way possible. And without further ado, let's get into today's topic, the Earth cycles. So, my head. It's always right in the way. Just put me up here for a quick second. So, we're going to be talking about the oxygen, the carbon and carbon dioxide cycles. More importantly, the carbon dioxide and how it relates to carbon and oxygen in general. We're also going to touch on the nitrogen cycle a little bit just because they're so interrelated. And I'll throw me back down here where I belong. This is just a funny little picture, by the way, also because cows are known for excreting, I guess, or emitting carbon based off of their feces. You wouldn't think it, but in Calgary in particular, or in other spots where there's just large cattle farms, there's actually enough fecal matter and farting and burping and all of that there's a significant amount of carbon being produced here. Okay, so the carbon cycle. You know what? Maybe I should just take my video off for now. You guys are not here to take a look at me. You're here to take a look at the information. So the carbon cycle is a complex arrangement of living and non-living elements on the Earth. Living humans and animals breathe carbon dioxide as we exhale, known as respiration, and we send it into the atmosphere to be absorbed and turned into oxygen once again by the plants and vegetation, known as photosynthesis. You can see this basically on the photosynthesis right here, as well as, microbial respiration decomposition is kind of what's factoring into like respiring. The main concern is that we also burn fuel, which creates carbon dioxide at an alarming rate beyond what the planet is capable of absorbing. The excess carbon dioxide is built up and stored in the atmosphere, where it becomes an insulator trapping heat from the Earth's surface. This heat is what's called global warming. So the carbon cycle is the process, as I said, which carbon travels from the atmosphere into organisms in the earth and then back into the atmosphere. Plants take carbon dioxide from the air and use it to make food. Animals then eat the food, and the carbon is stored in their bodies or released as carbon dioxide through respiration. So if we take the industry, which you can see over on the side here, out of the picture, it kind of looks like a natural process, right? You've got the carbon dioxide in the air. It gets eaten up basically or breathed in by the plants for photosynthesis. It's exposed, it's taken out as organic carbon and eaten by plants and animals. And then the animals and plants actually respire it back out into the environment as carbon dioxide again. And so someone looking at this diagram might then say, but Michael, why is it showing plants expelling carbon dioxide? They absorb carbon dioxide. And you're right, they do absorb carbon dioxide, and they use it in photosynthesis to produce energy with oxygen as an end result. Everybody's pretty familiar with the idea of photosynthesis. The photosynthesis is the important part here, though, because without sunlight, plants can't actually undergo photosynthesis, so they can't actually use carbon dioxide to produce energy and oxygen. A plant still needs to breathe, as it were, though, even though, so like during the night, it still needs to be able to breathe. So it actually breathes oxygen at night and breathes out carbon dioxide, meaning that a plant during the night will actually respire just like we do. Just a little interesting note there for you. So very briefly, I'm not going to get too much into the chemistry. This is what respiration and photosynthesis kind of look like. Respiration being on your left and photosynthesis being on your right. Respiring is what we do. We breathe in oxygen, as you can see here, and we combine that oxygen or use it with oxygen. And as a result, you get carbon dioxide and water as your products and energy, which we use to live. What's interesting is photosynthesis is kind of the polar opposite of this. You can see carbon dioxide and water on the left-hand side here, as before it was kind of the product. Here it's the starting point. And with the process of sun's energy and with chlorophylls in the plant cells, you get photosynthesis occurring and you get sugars and oxygen as a result. The sugars, of course, being used by the plants for energy and the oxygen being released back into the environment. So the carbon cycle is the biogeochemical cycle by which carbon is exchanged among the biosphere, the pedosphere, the geosphere, hydrosphere, and the atmosphere of the Earth. In this diagram here, human use is emitting 9 more units of carbon emissions. In the normal flow of the carbon cycle, as shown in that previous slide, respiration from animals, microbes, plants emits carbon into the atmosphere. And you can see that again through here, this 60 that's being appeared. Excuse me. The addition of human emissions can be slightly offset by the natural cycle. In this example of the 9 units that human use is producing, 3 is gathered up by plants in photosynthesis. So you can see the plants are respiring, the microbes and us are respiring, making up 120 total, right? 60 plus 60, there's your 120, and there's the 3 from the fossil fuels. I know there's a 9 total, but we're taking 3 of it that the plants can take in too. That still leaves us with 6 units that are unaccounted for, right? 9 minus 3 equals 6. Since the atmosphere is a global thing, not just a terrestrial job after all, the phytoplankton in the sea also help offset some of the carbon produced by man. However, as you can see, they're only able to actually absorb 2 units. So they respire and there's decomposition of carbon, and you get 90 here being released, 90 being uptook, as well as an additional 2, but that still leaves us with 4 as a kind of annual increase in the environment. The number themselves are not actually the important part, it's just to illustrate a point. What's important to gather from this is that the natural cycle cannot accommodate the carbon that humans are now emitting into the atmosphere. It's a natural cycle that has had an unnatural addition to it. It can certainly deal with a little bit, as shown by kind of taking that 9 and reducing it down to 4, but it can't eliminate all of the emissions we are adding. So here's the first layer that we mentioned briefly. We also mentioned it a couple of weeks ago. We went over the atmosphere in its 5 layers: the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. Can anyone remember the differences between each of these layers? Next up, we have the biosphere. So the biosphere is the layer of the planet on Earth where life exists. It's made up of living organisms and the physical environment, so it's also comprising the non-living components such as the rocky substance of the Earth's crust, water, light, and the atmospheric gas. It's kind of an all-encompassing thing. Next up, we have the pedosphere. The pedosphere is the outermost layer of the Earth that is composed of soil and subject to soil formation processes. The pedosphere lies below the vegetative cover of the biosphere and above the hydrosphere. And then your next question is probably, what's the hydrosphere? Well, hydro is kind of the giveaway for that. You can also see in this picture here that it also shows a cryosphere, which is basically the frozen water part of the Earth system. And then there's also, at the bottom here, the asthenosphere. The asthenosphere is the denser, weaker layer beneath the lithosphere here and makes up the upper mantle of the Earth. The two of them together, the lithosphere and the asthenosphere, make up what's called the geosphere. The geosphere is a scientific name for the solid parts of a planet. So, as I mentioned, it includes the lithosphere, which is the crust, and the uppermost mantle, which is the asthenosphere. And then finally, we have the hydrosphere, which I alluded to a little bit ago. The hydrosphere is the part of a planet that's made of water. So your oceans, your rivers, lakes, clouds, they're all typically included in the hydrosphere. In fact, the cryosphere probably could be part of this as well, just because technically ice is another form of water. The watery parts of our planet, including vapor that hover above the Earth's surface and water that's underground, they also make up our hydrosphere. So aquifers are also included here. So carbon is the main component of biological compounds, as well as a major component of many minerals like limestone. Limestone is a very useful compound with many purposes. One fascinating one that it has, it actually can help control acidity in water. So calcareous, by definition, that's what limestone does, it's calcareous sediments, is partly composed of calcium carbonate, in other words, containing lime or limestone. And again, I'm not going to get too much into the chemistry of this, but if you're curious how limestone acts as a buffer to control acid in water, this is how. So the calcium carbonate here, the CaCO3, is our limestone, and the HCl is our acid. To skip a lot of the process, acid in water is shown as the HCl, or hydrochloric acid. When this acid comes into contact with calcium carbonate, which is their limestone, the acid is broken down. The calcium component basically takes the chlorine from the acid and forms a salt called calcium salt, calcium chloride. Instead of it being sodium chloride, a salt that everyone is probably familiar with as the salt we put on our food, we get calcium chloride instead. The hydrogen molecules from the acid, as well as the oxygen from the limestone, actually form carbon dioxide and water with the leftover oxygens. If you're an eagle-eye spotter, you'll notice this equation, as it were, balances out. Everything on the left side of the arrow actually matches up and is accounted for on the right side of the arrow. So, for instance, there's 1 calcium, there's 1 carbon, there's 3 oxygen, that's what the 3 is there for, there's 2 hydrogen, and then there's 2 chlorines. The big 2 means there's 2 of each of these. And in the same deal, there's 2 Cls, there's your 1 calcium, there's your 1 carbon, there's 2 and 1 oxygen, and there's 2 hydrogen. It's all balanced out. So volcanoes are a natural cause of greenhouse gases. If you weren't aware of this, they are. They're part of the stabilization of the atmosphere over centuries of carbon cycling. Scientists claim that they are involved in the oxygen-rich atmosphere we have today by balancing the carbon dioxide and oxygen cycle that exists today. When volcanoes erupt, they vent the gas to the atmosphere and they cover the land with fresh silicate rock to begin the cycle again. At present, volcanoes emit between 130 and 380 million metric tons of carbon dioxide per year. For comparison, humans emit about 30 billion tons of carbon dioxide per year, 100 to 300 times more than volcano. Remember, there's that billion versus million, just by burning fossil fuels. Chemistry regulates this dance between ocean, land, and atmosphere. If carbon dioxide rises in the atmosphere because of an increase in volcanic activity, temperatures will rise, leading to more rain, which dissolves more rock, creating more ions that will eventually deposit more carbon on the ocean floor. It takes a few 100,000 years to rebalance the slow carbon cycle through chemical weathering. Mount Vesuvius, which I've had the pleasure of seeing in person, is a volcano near the Bay of Naples in Italy. It's hundreds of thousands of years old and has erupted more than 50 times. Of course, it's quite famous for an eruption that took place in the year 79 AD when the volcano buried the ancient Roman city of Pompeii under a thick carpet of volcanic ash. It's a so-called stratovolcano that lies to the east of what is now Naples, Italy. So a stratovolcano is a tall, steep, conical structure that periodically erupts explosively, and they're commonly found where one of Earth's plates is subducting below another, producing magma along a particular zone. Vesuvius' most famous eruption is the one that buried the Roman towns of Pompeii and Herculaneum in rock and dust in 79, killing thousands. The ashfall preserved some structures of the town, as well as skeletons and artifacts that have helped archaeologists better understand ancient Roman culture. Vesuvius is also considered by some to be the most dangerous volcano in the world today, as a massive eruption would threaten more than 3 million people who live in the area. The volcano last erupted in 1944. And as I said, I was fortunate enough to be able to go there, so I know for a fact that there are people that live close to the volcano. So the carbon cycle, this is actually a picture showing the nitrogen cycle. As you can see, there's nitrification, nitrates, and all that. Along with the nitrogen cycle and the water cycle, the carbon cycle comprises a sequence of events that are key to making Earth capable of sustaining life. We've got a video here that I'll share with you.
So last weekend, my family bought something pretty cool. Something I'm sure that you've always wanted. No, it's not a pony. It's a rotating compost bin. Yes, it's for compost and it rotates, which is going to be so awesome because the rotating part, that allows it to get aeration. You may already know about compost. It's where biodegradable things can decompose, and the whole idea is, after decomposing, the result is this nutrient-rich organic material that you can provide your plants with. So I'm thinking after a while of adding leaves, banana peels, grass clippings, twigs, overripe fruit. I could keep going. After all these items break down and decompose, I'm hoping to get some nutrient-rich material for my plants. So why am I even talking about this? Well, there are two major things that compost can supply plants with that are so important: carbon and nitrogen. We're going to spend some time talking about these two elements and their cycles because both of them are so important for life. With so many incredible elements on the periodic table, we don't know if it's really fair to have a favorite, but we do. It's carbon. Sorry, nitrogen, you're cool too, but why the love for carbon? Well, we really love how versatile it is. In one form, it could make up your pencil lead, which really isn't lead at all, it's graphite. It's a form of carbon. In another form, carbon can make up one of the hardest substances, diamond. The big four biomolecules, carbohydrates, lipids, proteins, and nucleic acids, they all have carbon. In fact, molecules that contain carbon are known to be organic molecules. Organic chemistry is a branch of science that studies the interactions of molecules that contain carbon. Just look at this carbon atom. Just look at it. It has 4 valence electrons, and carbon has the ability to form tons of compounds. Carbon is a building element in life for this reason. Well, now that you get the point on how important carbon is, let's make sure we understand how we get carbon. That means we need to take a look at how carbon can cycle. First, it's important to understand that there are carbon reservoirs, basically areas where carbon can be found, where carbon is hanging out. And the carbon cycle is a cycling among these reservoirs. So here are some major examples of where carbon is found. Carbon's dissolved in the ocean, it's in rocks, it's in fossil fuels, it's in living organisms, it can be found in the atmosphere. So the idea is to understand that carbon cycles among these reservoirs. Now, our time is limited, so let's take a look at one pathway. Consider carbon dioxide in the atmosphere. It's taken in by organisms that perform photosynthesis. This may be plants, it could be algae in the oceans or lakes, the carbon becomes a part of that photosynthetic organism. If the photosynthetic organism is eaten by an animal, it becomes a part of that animal too, and the animal that eats that animal. Both the plants and animals do cellular respiration, which releases carbon dioxide. When the plants and animals die, the carbon they contained can be stored in sediment, and over a long period of time, they can even be converted into fossil fuels. Now, the burning of fossil fuels produces a lot of carbon dioxide, but too much of that leads to the concern of excessive carbon dioxide in the atmosphere. See, carbon dioxide is a greenhouse gas, which means that it can trap heat in the atmosphere, so too much carbon dioxide is not a good thing. Now, what about nitrogen? Well, nitrogen is a critical element in amino acids. Remember, that's the monomer of proteins. And it's also an element in nucleotides, which are the monomers of nucleic acids. And if you remember from our biomolecule video, proteins and nucleic acids are two very important biomolecules for life. Nitrogen is kind of a big deal in the atmosphere, considering it's the primary gas in the atmosphere. The thing about nitrogen is that it's much more useful to organisms when it's fixed into other more usable forms. Nitrogen can be fixed by bacteria, which could be living in the soil, or even in the roots of some types of plants, where the bacteria live in symbiotic harmony inside the roots, meaning the bacteria get a home in the plant root and the plant gets the benefit of this fixed nitrogen. Now, once again, we're just looking at one pathway here in the nitrogen cycle, so keep in mind this is just one way for nitrogen to cycle. Okay, so let's take a look at this nitrogen in the atmosphere. Consider the type of plants that have nitrogen-fixing bacteria living in their roots. The nitrogen is fixed by those bacteria in a form of nitrogen known as ammonia and ammonium. Nitrifying bacteria in the soil can convert the ammonium to nitrates and nitrites, forms of nitrogen that plants can also easily use and assimilate. Now, animals can eat those plants and obtain that nitrogen. When both plants and animals decompose, decomposers return ammonia to the soil in a process called ammonification, where it can be used and reused again. But not all the nitrates and the nitrites get assimilated by plants. No, there are other types of bacteria in the soil too. Drum roll. Denitrifying bacteria. And denitrifying bacteria in the soil can convert the nitrates and the nitrites back into atmospheric nitrogen gas. Again, this is one example of nitrogen cycling through. Keep in mind this happens in both aquatic and terrestrial environments, and there are other ways for nitrogen to be fixed and to cycle. You know how we mentioned that too much carbon dioxide can be problematic? You want a balance in these cycles. Well, there's a balance for the nitrogen cycle too, and nitrogen pollution can be problematic. Here's one example. Consider plant fertilizer. Plants love it. It contains a form of nitrogen. Well, if it's not used responsibly, the excess nitrogen in fertilizing crops can drain into bodies of water. And one reason this could be harmful is that it will basically cause an aquatic producer heyday. All of the algae and water plants, they now have this crazy load of nitrogen for growth. And that might sound like a good thing, but all this producer excessive growth, it's messy. It can block light to the water, and then when they die and decompose, all that decomposing uses up a lot of dissolved oxygen in the water, which can be harmful to aquatic life who needs the oxygen. Whew. Now, you know, this recycling of carbon and nitrogen is pretty remarkable. Just think, you could contain a carbon atom that was once part of a dinosaur because of all this recycling. And the carbon and nitrogen cycle is just another beautiful thing connecting all of us. Well, I better get back to my compost. That's it for the Amoeba Sisters, and we remind you to stay curious.
Well, that took some of my thunder with some of my thoughts, but it's an interesting video based on the carbon and nitrogen cycles. Moving right along. Where's my mouse? There's my mouse. So, as I mentioned, along with the nitrogen cycle and the water cycle, the carbon cycle comprises a sequence of events that are key to make Earth capable of sustaining life, as that video actually does a very good job of indicating. It describes the movement of carbon as it is recycled and reused throughout the biosphere, as well as long-term processes of carbon sequestration and to and from carbon sinks. So, carbon sequestration is the process of capturing, or sequestration, I'm probably butchering how to pronounce that, is the process of capturing and storing atmospheric carbon dioxide. It is one method of reducing the amount of carbon dioxide in the atmosphere with the goal of reducing global climate change. The removal and storage of carbon from the atmosphere is absorbed in carbon sinks, such as oceans, forests, or soils, through physical or biological processes such as photosynthesis. So, nature has a natural way of storing carbon and carbon dioxide through photosynthesis. So, as I showed in that chemical equation earlier on photosynthesis, carbon dioxide is taken in with water and sunlight to form sugar and oxygen. Only the oxygen leaves the plant though, so all of that carbon is transformed from carbon dioxide into sugar for the plant to use. It's literally been sequestered and stored away for use by plants. Other ways carbon is stored is by organic decomposition, which slowly over many years turns into fossil fuels. Everyone is probably familiar with this example, as it's probably a T-Rex that's currently powering our cars. It's those fossil fuels that we extract from the ground to turn into the gas that we use. Calcium carbonate in the oceans are created when carbon dioxide in the water mixes with calcium ions. So that kind of shows you just a brief example of a couple of these, like the organic decomposition and the marine deposits of calcium carbonate, as well as the photosynthesis we see here. However, we're mankind, right? We always try and find ways to do things that nature does, or we just try and improve on things, or we just try and fix our mistakes. So there are man-made ways and processes to do sequestration. I don't know. I'm just not going to say that word anymore. Ourselves. So in a nutshell, an artificial way refers to a process whereby carbon emissions are captured at the point of the product's formation and then buried. One method is geological in basis, as shown in the above images. Basically, the carbon dioxide is pumped into underground chambers such as old oil reservoirs, aquifers, and coal seams that are unable to be mined, just storing the carbon dioxide in those spots as well. Another example, not exactly shown here, since this image just shows more of the idea of storing in aquifers, is placing the carbon dioxide by injecting it deep into the ocean, deep in the water itself still, but so deep down that the CO2 actually forms a lake. In theory, the carbon dioxide would stay down deep due to the pressure and temperature of the surrounding water. This carbon dioxide would gradually dissolve into the water over time along its periphery. There are possible dangers with this, as I will outline in a quick case study. If anybody's familiar with the Lake Nyos incident, then you know exactly where this is going. The Lake Nyos is one of only 3 lakes in the world known to be saturated, and I mean saturated with carbon dioxide. There was a limnic eruption, which occurred in 1986, and what happened was several 100,000 tons of CO2 was released. A limnic eruption is basically known as a lake overturn, where dissolved carbon dioxide erupts from deep lake waters. Triggers for this are believed to be earthquakes, volcanic activity, or other explosive events of those nature. The reason why this lake has so much carbon dioxide and is saturated was because there's a magma chamber beneath the region, which is a constant source of carbon dioxide seeping up through the lake bed. As a result of this limnic eruption, several 100,000 tons of carbon dioxide was released. This carbon dioxide actually spilled over the northern lip of the lake into a valley and entered nearby towns. Carbon dioxide actually stayed along the surface as opposed to just, spreading out throughout the atmosphere. And as a result, it killed over 1,700 people as well as livestock just by suffocating them. It was an unfortunate, truly terrible event that people had little to no warning for. And it's just, I'm not saying that's something that would necessarily happen if we were to sequester carbon dioxide in oceans or deep down in lakes, but it's something to keep in mind and something to be wary of as well. It just shows that we might have technology to do things, but we need to be fully cognizant of possible problems or things that could happen if we're not careful.
Carbon capture and storage explained. The U.S. Congress's recently passed budget bill includes incentives to support CCS, or carbon capture and storage. But what exactly is this technology? Fossil fuels supply most of the world's energy needs, but harnessing them emits large quantities of carbon dioxide that can cause irreversible environmental damage. One solution to combat this is carbon capture and storage, which works by first separating carbon dioxide from other gases at industrial facilities. The captured carbon dioxide is transported using underground pipelines or via ships to suitable storage sites. It is then injected into rock formations several kilometers below the surface of the Earth, where pressure and temperature conditions keep it in a liquid state. CCS can capture up to 90% of carbon emissions from fossil fuels, but experts believe it's most effective alongside other strategies, such as improving energy efficiency and switching to renewable energy. Take that, carbon dioxide.
Carbon turned to stone in climate change breakthrough. Researchers in Iceland are hailing a potential game changer for climate change after successfully converting carbon to rock. The project could help to reduce global warming by burying the waste CO2 produced by burning fossil fuels. Scientists at the Hultasheyri geothermal power plant in Iceland have converted carbon dioxide into the volcanic rock basalt. Researchers pumped 230 tons of CO2 into rock 500 meters underground, dissolving the gas in water to prevent it from escaping. More than 95% of the gas turned to stone within 2 years, speeding up a natural process that takes hundreds or thousands of years. A potential problem for the technique is that it requires 25 tons of water for every ton of buried CO2. However, researchers say seawater can be used, which is abundant at coastal sites. The project is seen as an improvement on existing carbon capture and storage methods that store CO2 as a gas, causing concern about potential leaks.
Researchers use sunlight to change carbon dioxide into ethanol. There's way too much carbon dioxide in the atmosphere, but some wicked science coming out of Cali may change all that. Scientists at the Berkeley Lab in California have developed technology that can convert carbon dioxide into ethanol using sunlight. This process is known as artificial photosynthesis. During photosynthesis, plants use light from the sun to create food and oxygen. Low amounts of solar energy were used in a copper-silver nanocoral cathode to produce ethanol. The researchers said their process used around 2.5 volts, half of what it currently takes to turn CO2 into ethanol.
A carbon dioxide-sucking plant just opened in Zurich. The alarming rise in atmospheric carbon dioxide has led scientists to develop removal technologies to counter climate change. One such company in Switzerland has built a plant that directly removes this carbon dioxide from the atmosphere. The Climeworks plant is located on top of a waste recovery facility, which provides it with heat and electricity. Air containing carbon dioxide and other molecules are blown through several carbon dioxide collectors. The plant currently has 18 such collectors, which are large boxes fitted with filters that capture more than 2,400 kilograms of carbon dioxide each day. Carbon dioxide binds to the amines in the filter, while other molecules pass through and return to the atmosphere. Once saturated, the filter is heated to 100 degrees Celsius, causing the carbon dioxide to unbind and be extracted. The filtration system can be reused several thousand times, allowing this process of removal and collection to be a continuous cycle. The carbon dioxide collected by the plant can be stored underground, used to help make renewable fuels and materials, or supplied to the food and beverage industry. Climeworks provides 900 tons of carbon dioxide annually to a nearby greenhouse, which has reportedly increased their crop yield by 20%. Climeworks also hopes to remove 1% of global carbon dioxide emissions by 2025.
A power plant that takes away carbon emissions. Say hello to the world's first negative emissions power plant. The geothermal plant in Iceland, in cooperation with Climeworks, will remove an estimated 50 metric tons of carbon dioxide from the air each year. The process works by pulling carbon dioxide from the ambient air using a special filter. The heat from the power plant warms up the filter, which extracts pure carbon dioxide. The gas is then combined with water and pumped 700 meters underground. When the carbon dioxide reaches basaltic rock, it forms minerals. The project is still in the pilot phase, but researchers at Climeworks believe negative emissions plants could be set up around the world. One major obstacle in place is the price. Climeworks estimates it runs around $600 to extract 1 ton of carbon dioxide from the air. However, if economies of scale can be utilized and more plants open up, that price would drop significantly.
So there is definitely some light at the end of the tunnel here, right? There are definitely some ways that we can sequester carbon dioxide in safe and manageable ways. The issue is always money, as that last point kind of brings up. This is kind of funny. Where was I just lost my train of thought seeing that. If it comes back to me, I'm sure I'll bring it back up. So this is global warming in a nutshell with this chart, right, that we're showing right here. Essentially, as carbon dioxide concentrations increased, temperature of the surface also increased. If you use the 20th century as a baseline, you can see that carbon dioxide concentrations have continued to increase globally. Not coincidentally, the average temperature has also increased. It looks like at this moment, around 2020, we have increased our carbon dioxide to over 400 parts per million in the atmosphere. As well, the average temperature has increased to roughly 1.2 degrees Celsius hotter than the 20th century. 1.2 degrees might not seem like much of an increase, but that's the average global temperature we're talking about. Tipping points could be reached between 1 and 2 degrees of warming. In week 11, we'll be going over climate change as a topic, so I'll only really skim over some stuff right now. So greenhouse gases are obviously bad in a large quantity, but they're good in lower quantities. This is kind of a saying when you get to poisons and toxins and stuff like that, where the dose makes the poison. The amount is what's actually making the problem. Greenhouse gases like carbon dioxide are actually the reason why the Earth is habitable in the first place. These gases act like a thermostat to capture just the right amount of heat from the sun to keep an average 15 degrees Celsius over the globe, on average. Just the right amount of solar heat is a finicky thing. If you have too little greenhouse gases, too much heat will escape into the atmosphere or into space. Too much greenhouse gases, and then we boil, which is kind of shown from the far right over here. The greenhouse gases in our atmosphere are what regulate our temperature here on the surface. The gases create a delicate mix of carbon dioxide and the carbon cycle to allow the right amount of sunlight to have contact with the surface and then insulate it from leaving into the atmosphere. As the amount of greenhouse gases increases, so does the temperature over the Earth, because with more greenhouse gases, they're able to insulate more of the heat from leaving. It's kind of a neat little case study where the planet Mars has a very thin atmosphere, but that atmosphere that does exist is nearly all carbon dioxide. Because of the low atmospheric pressure and with little to no methane or water vapor to reinforce the weak greenhouse effect, Mars is largely a frozen surface that shows no evidence of life. If you compare that with Venus, which like Mars is also an atmosphere of nearly all carbon dioxide, but Venus has about 154,000 times as much carbon dioxide in its atmosphere as Earth, and about 19,000 times as much as Mars does. This produces a runaway greenhouse effect and a surface temperature hot enough to melt lead. Not a good place to go vacation. There's a group called the Intergovernmental Panel on Climate Change, and they're a group of 1,300 independent scientific experts from countries all over the world under the watchful eye of the United Nations. They concluded that greenhouse gas increases over the past 50 years have warmed our planet. Since the Industrial Revolution started, humans have been largely increasing the levels of carbon dioxide and other greenhouse gases due to the burning of fossil fuels. If we were to go back to this chart here, you can see that it's really around the 1940s, 1960s, and so on, where we actually start seeing a dramatic increase in the amount of carbon dioxide concentration being released in the environment. The industrial activities that our modern civilization depends upon have raised atmospheric carbon dioxide levels from 280 million parts per million to 400 parts per million in the last 150 years. The panel also concluded there's a better than 95% probability that human-produced greenhouse gases such as carbon dioxide, methane, and nitrous oxide have caused much of the observed increase in Earth's temperatures over the past 50 years. I'm a little bit of a betting man, so I would bet that they're correct and that the human-produced greenhouse gases are the reason why Earth's temperatures have been increasing. To further on to that, if the warming were caused by a more active sun, then scientists would expect to see warmer temperatures in all layers of the atmosphere. If you recall from an earlier lesson, we've gone over the different layers of the atmosphere. Instead, they have observed a cooling in the upper atmosphere of the exosphere and a warming at the surface and in the lower parts of the atmosphere. That's because greenhouse gases are trapping heat in the lower atmosphere, which is what they're part of their job, part of what they do. We just have too much of it. On average, Earth will become warmer. Some regions may welcome warmer temperatures, but others may not. All environmental agreements are accepting that the Earth's surface temperatures are going to increase in the future. The Montreal Protocol and Paris Agreement envision a 2-degree average increase over the next few decades, and many think it won't stop there. Once we actually get into the climate change presentation, we'll go over what this kind of information means and what 2-degree average increase would actually do. For now, don't worry about it. This is all you need to know at the moment. And we'll finish with a nice TED Talk.
The term climate change carries a lot of emotion. Guilt, anger, frustration, fear, but rarely any feelings of hope or accomplishment. And never any pride, and of course it doesn't. We're bombarded every day by images that seem to have only one conclusion. We're all just screwed. We're screwed, and there's not a lot we can do about it. Scientists are telling us that we're ruining the planet. You and I are ruining the planet every day by just living our lives. They're saying that we're to blame. But it's so hard to see anything that we can do to change that. I mean, I guess there are obvious things. We could live without electricity or heat and ride a bicycle everywhere. But if everyone did that, most things in our society would have to change anyway. And where do we even start? It feels pretty hopeless. But I've been working on solutions to climate change for 10 years, and I'm here to tell you that it's not hopeless. We have the power to stop climate change. You and I do right now. I'm not talking about changing light bulbs or buying more efficient refrigerators. I mean actually stopping climate change. We have the power. We've just lost sight of our power, and in order to find it again, we need a new paradigm. We need a new perspective that shows us exactly what we can do every day to fight climate change. Now, it's going to take some work to get there. We're going to have to dig through some science, but when we come out the other side, you'll know how to cut your carbon footprint by 60% today. Our new perspective has 3 parts. First, we need to know about green carbon. Then we need to know about fossil carbon. And finally, we need to know about green carbon versus fossil carbon in our modern world. So let's get started. First, green carbon. Green carbon is all about carbon dioxide. And carbon dioxide gets a lot of press these days. We hear about it coming out of our tailpipes. We hear about it coming out of our smokestacks. We hear about it causing climate change. But the truth is more nuanced than that. The Earth's atmosphere has almost always contained carbon dioxide, and that's a good thing because without carbon dioxide, our planet would be a lifeless, frozen hunk of rock like Mars. We need carbon dioxide to create the natural greenhouse effect, the greenhouse effect that keeps us from freezing, and that's really important. But even more than that, we need carbon dioxide because of something called the carbon cycle. Now, the carbon cycle is the beating heart of our planet. On geologic timescales, the carbon cycle is what sets the Earth's temperature like a thermostat. It balances the air and the rocks and the oceans and determines how hot it's going to get here. But on a day-to-day timescale, the carbon cycle is what allows complex life forms like us to exist in the first place. We wouldn't be here without the carbon cycle, and it all depends on carbon dioxide. And that's the same carbon dioxide that you're breathing out right now. Because we breathe in oxygen and breathe out carbon dioxide, and plants do the opposite. They breathe in carbon dioxide and breathe out oxygen, and that's crucial because plants are actually building themselves molecule by molecule out of carbon dioxide in the air and the energy of the sun. Plants are literally made of air and sunlight. You can see this happening in your home every day. Every one of your houseplants is making itself molecule by molecule out of the energy coming through your windows and the air in your home. If they were making themselves out of the soil in their pots, the soil would disappear as they grow. But that doesn't happen because plants are made of air and sunlight. They're the start of the carbon cycle. And then it goes like this. First, green plants capture carbon from the atmosphere and the energy of the sun. Then animals eat those plants to take that carbon and energy, because animals are made out of carbon and energy of the sun too. They just take it from plants. Then other animals eat those animals, on up the food chain, till eventually an animal does not get eaten, dies naturally, and then decomposition releases its carbon back into the atmosphere to start the cycle all over again. Decomposition is what balances the carbon cycle. It makes sure that the carbon that goes in comes back out again on the other side, and that it all forms a closed loop, just circulating the carbon from one side to the other. Now, there's a cycle like this that happens in the oceans. There's a cycle like this that happens in the soil. All of this carbon I call green carbon. Green carbon is the carbon that's supposed to be here. It's the carbon of living things. It's the carbon of the carbon cycle. It's the carbon of our climate. Green carbon does not cause climate change because it can't cause climate change. It already is our climate. It's already a part of our thermostat. Fossil carbon is what causes climate change. Now, climate change is a huge issue. There are all sorts of contributing factors, but this is the big one. Fossil carbon is the main cause of climate change. If we can stop releasing fossil carbon, we can turn the tide of climate change. And in order to do that, we need to understand it. We need to know about its origin, and so we need to go back in time. And we can go back to any number of places in the Earth's history, but we're going to go back and visit the dinosaurs. And the first thing we notice when we get there is that there's a whole lot more carbon dioxide in the atmosphere. This is the late Jurassic period, and there's 7 times as much CO2 in the atmosphere as the Earth today. It was hot. But the carbon cycle operated just the way that ours does. First, green plants capture carbon from the atmosphere and the energy of the sun. Then animals eat those plants to take that carbon and energy. Then other animals eat those animals, on up the food chain, until eventually an animal does not get eaten, dies naturally, and then decomposition releases its carbon back into the atmosphere to start the cycle all over again. At least that's how it was supposed to happen. There was a problem. Decomposition stopped working very well. Decomposition needs oxygen in order to function correctly. It's the great recycler. It's what makes sure that what goes in comes back out of the carbon cycle again. But under the right circumstances, in swamps and in shallow seas, zones without oxygen can develop. We see this on our planet today in our swamps and in the algae blooms like the one off the coast of California right now. Algae, green stuff, grows so fast that it sucks up all the oxygen out of the water beneath it. If something dies in that water, decomposition doesn't have the power to break it apart completely. Instead, it sinks to the bottom, partially decomposed, and still full of a lot of its carbon and energy. Well, in the late Jurassic period, the Earth was covered in swamps and shallow seas. And so carbon drained out of the carbon cycle. It formed huge reservoirs of undecomposed organic material full of carbon and energy. The carbon cycle was off balance. Eventually, circumstances would change and the carbon cycle would right itself again, but there was less carbon to go around, and so the carbon cycle had to evolve to a world of less carbon, and that takes about 100,000 years. In the meantime, all of the carbon in those reservoirs slowly sank into the earth, where heat and pressure transformed it into coal, oil, and natural gas. This is our fossil carbon. Fossil carbon is the carbon of fossil fuels. Fossil fuels only burn because the energy stored in carbon molecules by million-year-old plants. Basically, fossil fuel is million-year-old sunlight. Now, the heat and pressure underground concentrated that sunlight, so it's really potent and it burns really well. That's why we like it so much. But when we release that energy and burn that fuel, we also release the fossil carbon that contains it. And that's the problem. Because if we come back to our Earth today, we'll see that our carbon cycle is balanced the way that it is. The amount of carbon that goes into the carbon cycle comes back out again. It's all a closed loop. So when we burn fossil fuels and release all of their fossil carbon, it goes up into the atmosphere and has nowhere to go. It can't just join into the carbon cycle again because the carbon cycle is a closed loop. It can only take in so much carbon. And so instead, it stays in our atmosphere where it unnaturally increases the greenhouse effect, acidifies our oceans, and causes climate change. This is the cause of climate change. Now, eventually, 100,000 years from now or so, our carbon cycle will also adapt to all of this new carbon. But in the meantime, we're screwed. We are burning million-year-old sunlight by the barrel everywhere on Earth. We just love this stuff. The truth is, we're going to run out. Even if climate change were a hoax, if our society is going to survive, we have to switch away from fossil carbon and fossil fuels because we're going to run out. Climate change is just forcing our hand. And so what are our options? What can we choose instead of million-year-old sunlight? Well, there's the heat in the center of our planet, but it's difficult to access and occasionally unstable. There's our newfound ability to release atomic energy, but the byproducts are deadly and last for hundreds of thousands of years themselves. There's the moon's gravitational pull, creating ocean tides. There's a little energy in the spinning of the Earth and in gravity, and there's sunlight. That's it. Those are our 6 options, period. If our society is going to survive, we have to switch to these options. We don't have a choice. And of them all, sunlight offers by far the most energy. We can use it directly as solar radiation, we can use it indirectly as wind or waves, or we can use the energy stored in carbon molecules by green plants, because green plants are the original solar panels. They're what trapped the energy in fossil fuels to begin with millions of years ago. And the only reason we moved away from green plants is because the energy in fossil fuels is concentrated underground. But we don't need them anymore. Today, just about anything that we make out of fossil carbon, we can make out of green carbon instead. And when we do that, it can't cause climate change because it's already a part of the climate. It's already a part of our thermostat. This is a plastic bag that's made out of petroleum, out of oil. Millions of years ago, this was partially decomposed organic gunk at the bottom of the sea. This is a plastic bag that's made out of plants that were alive just a little while ago. They're both plastic. The difference is the source, and it's all about the source, because this one causes climate change, and this one doesn't. And you have the power to choose. You don't have to choose fossil fuels and fossil carbon. And when you don't, you can cut your carbon footprint incredibly. In 3 steps, you can cut your carbon footprint by 60% just by not choosing this, because we don't need it anymore. Step 1 is the easiest. It's your electricity. Right now, you can sign up with an alternative energy provider that will generate all of your electricity without releasing fossil carbon. Wherever you live, whatever your circumstances, if you get an electric bill, you can sign up with alternative energy today. It might be solar, it might be wind, it might be something else, but just this one step will cut your carbon footprint by 15%. By comparison, changing all of the light bulbs in your home to LED bulbs will only cut your carbon footprint by 0.2%. It's a big difference. Now, it can be hard to know what your options are, and if you need help, you can come to my website, jacksoncarpenter.com/electricity, type in your zip code, and find out what your options are. Step 2, heating and cooling your home. But we already have a head start on this because most cooling devices, most AC units, most heat pumps, most swamp coolers already run on electricity, and we've taken care of our electricity. And all that's left is heating our home in the winter. And likewise, if you have an electric heat pump, electric baseboard heating, or electric space heaters, you've taken care of that as well. And so you've cut your carbon footprint by 32% already. That's almost a third. But here's where it gets interesting. What if you don't have electric heat? Well, anything that you can use to heat your home that releases green carbon instead of fossil carbon will not cause climate change. So if your furnace runs on heating oil, you can go down to your local biodiesel distributor, there's one less than 10 miles from where I'm standing, and get a green carbon product called BioHeat. BioHeat's made of green carbon. It doesn't cause climate change, even if you burn it in your furnace. Or you can burn wood. Wood is made of green carbon. It doesn't cause climate change either if it's sourced sustainably. Now, wood or biomass is maybe the most contentious issue in climate change today. It is sustainable if you plant the seeds, let it grow, and then cut down the trees. We can't go into our forests and cut down our forests because that's disastrous for our climate. We need to replant our forests. But wood that's harvested sustainably as a crop is a great source of climate-friendly fuel. It won't cause climate change, even if you see smoke coming out of your chimney, because it's not about the smoke, it's about the source of the carbon. Step 3 is your car. Now, here's something that might be news to you. Every car on the road today has an alternative source of fuel. Every one, even your old gas guzzler. Just switching over will cut your carbon footprint by another 28%. So what options do you have? Well, if, like most people, you fill your car with gasoline, your green carbon fuel is alcohol. Your car will run on alcohol. The most common kind of alcohol fuel in the US is the same kind we like to drink, especially on spring break. It's ethyl alcohol or ethanol. Now, you can ferment ethanol from just about anything. Sugarcane or sugar beets are great sources of ethanol. But whatever you make it from, ethanol is made out of green carbon. It won't cause climate change even if it burns in your engine. Now, before you run out and fill up your gas tank with vodka, you do need to get real ethanol. And before you do that, you actually need to get an adapter to make your car into what we're calling a flex fuel vehicle. But most adapters cost less than $300 and take less than an hour to install. Most gasoline, ethanol is so compatible with gasoline, in fact, that most gasoline sold in the US already has about 10% ethanol in it anyway. So that takes care of gasoline. What if you have a diesel vehicle? Well, the green carbon alternative to diesel fuel is called biodiesel. You can put it in your tank and drive away. You don't even need a conversion. And these are only the two most available kinds of alternative fuels. There's a whole second generation of alternative fuels called drop-in fuels that should be available any day. And you have options. You have the power to choose another source other than fossil carbon. You can even choose a shiny new electric car as long as your electricity comes from a source that does not release fossil carbon. That's the clincher. If your electricity comes from coal, your car's carbon footprint will be as bad as your grandma's gas guzzler because it's all about the source. And that's it. Step 1, electricity. Step 2, heat. Step 3, your car. Altogether, we've cut 60% of your carbon footprint, and you didn't even have to buy a bicycle. No governmental plan comes anywhere close to that kind of a reduction, and that's the point. We can do this on our own. We don't have to wait for the government to act. And you don't need me standing up here telling you what to do either. Together, we've gotten to 60% of your carbon footprint. How can you go further? Well, just look to the source of things. Do your products come from green carbon or fossil carbon? Do you want paper or plastic? Or do you want a reusable cotton bag? Or do you want a plastic bag that's made out of plants instead of petroleum? You have so many options, and you have the power to choose. And you have the power to tell your friends. Tell your friends. They don't have to feel hopeless in the face of climate change either. Our future is one of hope and pride in the way that we've lived our lives. Everyone in this room has the power to choose that future today. You can just choose something other than fossil carbon. Your choice has never been more important. The world literally depends on it. Thank you.
I feel like that's a pretty good point to end off this talk on. I really like that thought of plants literally being made of air and sun. In a way, it's true when you go back to that chemical formula that I showed you earlier. That's it basically for this presentation. That wraps up to the end there. I just want to give another brief, quick reminder that the assignment for fighting climate change is due tonight at midnight. Essay 1 that I went over as well at the beginning of this presentation will be due next week, Friday, February 18th at midnight. And following that, the following week, our midterm will be conducted for the entire week. You get your one attempt. I'll go over and remind you guys again next week about the midterm coming up. Otherwise, if you have any questions, any concerns, anything at all, you can always feel free to reach me by email. I've been enjoying the contact I've had with you guys so far. Keep it up. I've finished marking everybody's assignment number 1 as well, so you guys can take a look at your marks for that. If you have any questions about any of that as well, about how I arrived at the mark or anything like that, please feel free to reach out to me for that as well. I guess, as I said, that's the end of it, so thanks for tuning in, and I hope you enjoyed this talk, and I'll talk to you guys again later.